Yeah, you are very much audible.
Right. Thank you so much. So I had two speakers that spoke about industrial things, and now moving on to research. Uh, the thing that I'm going to talk about is mineralization. So we are converting CO2 to a mineral product, and the idea is that at the end of the day, nature's way of mitigating CO2 is what is mineralization. Okay, so there's this one graph that was published in one of the perspectives by Professor Lankner in 2003 in Science. And this graph gives us a very good idea of how CO2 sequestration works. So if you look at it, it's the axis says the characteristic time of storage to the characteristic capacity of storage. And at the fag end on your right hand side on top, you find that the mineral carbonates exist. That is, it is the most favorable way of storing CO2 for a long time. So if you talk about the Grand Canyon in the US, the entire thing is a mineral carbonate deposition. And the best part with carbonates is that they're thermodynamically quite stable material. So we are looking at a material storage capacity at the end of the day, which can sustain. Secondly, we're looking at its applications in different things. So say, as Takashi just said, like you're looking at cement plants and reutilization of the CO2, which is being produced by the cement plants. These are at the end of the day going to turn into mineral carbonates and going to stay there. So carbonation helps us not only to keep the CO2 captured as a thermodynamically stable form, it also helps us to keep it there for a very long time. So if you look at the number of years that CO2 can be saved is something around about 10 raised to 5 years. Okay, so that's a very high capacity as far as longevity of captured CO2 is there. However, this is a very slow process. So we have two ways of looking at it. One is called as in situ mineralization. So we are pumping CO2 underground, and when we are pumping CO2 underground, they get dissolved within either the old unminable coal streams or saline aquifers or any such system, and they in the end get converted to mineral carbonates, and these mineral carbonates get deposited on the surface either of the mother rock or the bedrock, or they would go at the bottom of the aquifer and settle there. So this is something that we have been trying, and mainly the EOR systems tend to do it as a byproduct of the entire EOR process. So the petroleum industry has been using pumping CO2 down crude oil streams and pumping oil out. So at the end, what happens to that CO2 is it gets converted to a mineral carbonate. The other way of looking at it would be to industrially make this kind of mineral carbonate. So say you have any kind of industry that is there, like a power plant. What we tend to do is we pipe all this CO2 and some solid waste or some natural minerals. So what you see here are some solid wastes that can come, which can be waste product, mainly from the steel manufacturing companies, or it can be mineral carbonate, mineral material, something like olivine or wolstenine that can be brought in. You carbonate it to say either magnesium carbonate or calcium carbonate, and they can be used. They can be used for construction, and they can be used for land requisition as the temperatures are rising, sea levels are rising, land encroaching of the oceans becomes high, so we can requisite land accordingly. Now, when we look at this mineralization process, there are two major ways of looking at it. One would be I take the gas, that's the CO2 gas, and whatever is my solid mineral, and react it together. The other option would be that what I do is I take this gas and put it in conjugation with a liquid based source, something like something that you see in a saline aquifer, and mix them together and you get the mineral. With all these different technologies that are there, most of them are not up to the pilot plant scale. There are very few technologies in carbonation which have reached the pilot plant scale, and there is one technology that has been tried to demonstrate. However, commercial scaled projects are yet to become full-fledged applicable to other systems. So, what are we looking at? The major thing that we are looking at is the aqueous mineralization process. Because it is thermodynamically a bit more, uh, a bit more, uh, uh, the way to put it, it is a bit more attractive. And in also the thing is, this process actually is a natural mimicking of how the geobio cycle works. Okay, so the biggest challenge that we have is that within the geobio cycle, this is a really big, difficult thing to do because of its slow rate processes. So therefore, we now are looking at catalysts generally to help enhance both. Look at the mass transfer rates as well as the kinetic rates, in which whenever we are looking at the mineralization process, we are stuck up with three major challenges. The first one is the extraction of the metal ion. So if we are using artificial industrial waste, mainly the metallurgical wastes, we have a ready source of mineral ions that are there. However, whenever we look at the natural mineral rocks, we find it really difficult to remove all these metal ions from these rocks, and a lot of emphasis and impetus is given to extract this. That is our first major challenge. The second major challenge is the hydration of CO2 by itself. So that the best catalyst that we know for hydration of CO2 is called as carbonic anhydrase 2, or the human carbonic anhydrase 2, which is present in our lungs. And we are talking about rates that is 10 raised to 6 molecules per second. So that high kind of kinetic rate, nothing, no catalyst known to man can do this, but nature has created a catalyst to do that kind of job. However, utilization of that catalyst is very difficult because there are various ethical and other norms that come in. So people have been trying with other forms wherein you can extract this catalyst from waste material, something like slaughterhouse wastes, wherein you can extract this catalyst and use it. However, there are a lot of biomimics that have come for this, and I'll be discussing one of such mimics. Last but not the least is the actual precipitation of the mineral carbonates. Now, for this, we need something which is called as a sacrificial base. Means I need a basic material that would give that would accept the proton from the carbonic acid formation and precipitate all these mineral carbonates. Now, the options that we have are natural clays, and one of the biggest, again, we are looking at industrial waste, something like red mud, which is in high in pH and actually has very less applications because of its high pH. So we would like to bring their pH down. So you use it in processes, something like mineralization, wherein you're bringing the pH of these red mud down, as well as capturing CO2 and using it as a construction material. Now, when we are looking at hydration of CO2, the best known catalyst, as I've said, is carbonic anhydrase. So on your left, what you see are 4 different structures of the same enzyme. We call it A is the alpha phase, B is the beta phase, C is the gamma phase, and D is the delta phase. So there are actually 8 different types of catalysts, but 4 of which we have very good identification of how the structure looks like. On the right is something that we did at Newcastle, where I was doing my PhD work. And what we were working was with a nickel nanoparticle, which worked as a similar catalyst to that of carbonic anhydrase. And it is something that I'll be focusing more on the work that we did with nickel. So when we are looking at hydration catalyst, nickel became a very important candidate, mainly because it was an inorganic catalyst already being used highly in the hydrogenation processes. So we have a lot of expertise of working with nickel. Secondly, we could ramp it at atmospheric pressures and temperatures. We could work very nicely with it. We could find that if we are using it as a catalyst, not just for mineralization, but even the carbon capture process. So we, as Mr. Shah starting address, that the amine based capture processes are something that we have a lot of experience with. With our studies, we found that we could actually enhance the kinetic absorption capacity of amine solutions up to 33%, mainly with a primary amine and a tertiary amine up to something around about 32%. So we can actually still enhance and make the technology, the amine based technology, still more profitable. If we are not going for amine based technology, then we look at the carbonate based technology, which is another absorption technology which is available. So you can use the catalyst in two different things: mineralization as well as the enhancing the existing technology. We have tried to immobilize these catalysts. So we have been using nanoparticles, we have been suspending them. So rather than suspending them, let us try to work with it in a way that we can put it into a support and then use it. So we have tried with different kinds of aerogel systems, which are lightweight and easy to make. So one of my colleagues at Newcastle has his own way of making these aerogels, which are quite promising as an industrial method to produce aerogels. And with him, we were working on actually embedding nickel nanoparticles into this and testing its capacity for CO2 hydration and application. Now, coming to use of these nanoparticles for mineralization. So this is a work that was done in AU Leuven, and what they had done was they had a slurry-based reactor, and what they tried to do was convert CO2 to carbonate using calcium oxide as a raw material source, which is one of the major products that is coming out of the steel plants as a waste material. And they found that as they had these nanoparticles in, they had better yield efficiency. So the ones that you see in in the dark blue color are the ones that you see the efficiencies for the ones wherein you're using the nickel nanoparticles, whereas the ones which you see in green are the ones which it does not use the nickel nanoparticles. Then the other kind of work that we did at Newcastle was we developed something called as a tabular reactor. And in this, we were looking at CO2 mineralization, wherein we have a gas and a liquid. So what we were doing was we were taking, say, your saline aquifer waste or brine solutions generally, which is a waste of the desalination units, and trying to see whether that waste can be used for CO2 capture, both as a control and as with the help of a nickel nanoparticle technology. And over here that we land up seeing is with the help of the nickel nanoparticles, even at lower gas flow rates and having a good gas to liquid ratio, we can get better mineralization as compared to what we would see without the nickel nanoparticles being there. So in that case, you're looking at a very simple reactor, which is just a tubular type reactor, wherein you can actually bring down the CO2 from your flue gas stream and convert it to carbonate type structures, so that we can actually reutilize whatever is the waste stream. And the biggest problem with with the desalination waste is I cannot put it back into the ocean. So I need to bring, because it's a high pH value product which is being thrown out as a byproduct of the desalination plant. So if we can reduce down its pH by removing some of the calcium from the system, we can again send it into the ocean, and on the way also reduce CO2 from the system. However, for all these studies that we have done, we have always been using a predetermined CO2 composition, which is pure CO2 that we are getting from the in the lab. However, we have tried with artificial flue gas system, and we could see that even in the artificial flue gas system, the nickel nanoparticles do give us better results. So what are we talking about at the conclusion of this? Mineralization is a process that would help sequester CO2 for a long time as well as a high capacity. There are various different steps that are being used, and each one of them people are working to make it more make it more applicable and make it more sustainable. So here, generally people, what they're looking at from mineralization is if we can have a catalyst that can work in environment wherein I can utilize multiple waste streams and try to see if they are easily movable from one place to another, and that would help us develop an economical process wherein we can actually utilize these wastes along with the entire global warming scenario, wherein you're capturing CO2, managing waste, and creating a value added product, or creating a product that can actually be useful for some or the other application. Yet we are still not very close to our dream. So mineralization actually is a not the mineral product is not a very high value product that you get. So in that case, the actual commercialization of this entire process becomes economically challenging. However, yet we are trying to look at, say, a fast fluidized blade reactor or a slurry bubble column reactor, wherein we can do a lot of processing together and actually reduce the kind of plant-wide systems to one or two reactors that are combined together that can be easily put onto a, say, a power plant, as Mr. Shahid initially said, to have a power plant that is equipped to deal with this. However, the biggest challenge would be to get the mineral source, which is either, say, an alkali waste material from a process industry or from a mining industry to the power plant, or if they are very close by, it's very easy to work with, to find better alternatives for the enzyme or to make the enzyme system best way that can be done. Also, one has to still work out reactor design and all the transport processes associated with this. So at the end, I would like to thank Newcastle for some of the funding that we did for this work. IIT Jammu for the seed grant funding, which actually is a part of the ongoing projects that we are doing here. My supervisor, Dr. Lydia Schiller from Newcastle, and my colleague from IIT Kharagpur, Parag, and all the students that have worked in our labs, and mainly Dharmik, who's currently working with me for the carbon capture and mineralization project. Thank you so much for your time.